Welcome Archita, and it's my pleasure to welcome Archita Agrawal to our blockchain seminar. And Archita Agrawal is a graduate student in computer science department at Brown University, and she works in the area of applied cryptography under the supervision of Seni Kamara. And today she is going to give a talk on her latest results on the paper which was published. Sorry, I forgot the conference name. The title is Encrypted Blockchain Databases. Welcome, Archita. And now,
thank you.
The screen is yours.
Okay, so I'll just share my screen.
Yes.
Okay. Yeah, thank you, Veronica, for inviting me. It's actually a pleasure to present my work at the group. And yeah, the paper was published at AFT, which is Advances in Financial Technology this year. So yeah, the title of my talk is Encrypted Blockchain Databases, and it's a joint work with Daniel Atkins, who is an undergrad at Brown University. He's an amazing student. And Seni, who's my advisor, and Tariq, he was earlier working with Seni, but now he has his own startup. Okay, so let's start. So what are encrypted blockchain databases? So they fall at the intersection of blockchains and databases, and they try to guarantee the properties of both blockchains and databases. So they try to bring the best of both the worlds. So for example, they try to guarantee that you have decentralization, tamper-proof and auditability of blockchains. And at the same time, they try to guarantee low query latency and query expressiveness. What I mean by query expressiveness is that you can run different kinds of queries on the databases that you are storing on. You can run different kinds of queries on the data that you're storing in these blockchain databases. So these blockchain databases, people are already looking into it because they have such nice properties. So for example, these projects, these startups like BigChainDB and BlueZelle, they are already working on these kinds of databases. And the things that they want to do with these databases is that they want to store in them data that pertains to medical health records, financial records, legal documents, and so on and so forth. And you can, as you can already see, that this is very sensitive data. So of course, the question of then confidentiality arises. So what we actually need is that we need some sort of encryption on these data, these kinds of data, before we store them in the databases, right? So that because if the database is even public, the data is secure. So what we did in this work is that we looked at a very specific kind of data structures. We looked at encrypted multimaps, and we tried to analyze their design and their security, and came up with some algorithms of how we can store these multimaps on the blockchains. So you can also think of these multimaps. I'll define precisely what multimaps are, but at a high level, you can think of them as key value stores, which are also a kind of NoSQL databases. So if you work in distributed systems, you would definitely know what key value stores are. Actually, a lot of companies, they use key value stores big time to support their systems. For example, Amazon uses Dynamo, which is a key value store, and it is the basic building block of its cart. So you can imagine how prominent that is. Then Google uses another key value store, which is called big table. So like all the big companies have been using these key value stores to store their data. And multi-maps can be used to initialize these key value stores. So in this talk, what I will talk about is I'll start with introducing what multi-maps are. So precisely, I'll say what these are. Then I will define what encrypted multi-maps are. And then finally, I'll give you 3 constructions of how you can store encrypted multi-maps on blockchains. And then I'll talk about some real world deployments and some concerns that might arise because of these deployments. And finally, I will end my talk with some conclusion and some future work directions. Okay, and so we discussed this already, but again, if you have any questions, please raise your hand or maybe put it in chat, but I'm not monitoring the chat, so it'll be better if you raise your hand or just unmute yourself and ask the question. Okay. So what are multi-maps? So it's just a set of label value tuples. So here I've shown a picture. For example, L1 is a label and it has an associated tuple with 2 values, V1 and V2. Similarly, L2 is another label with an associated tuple with 3 values, V1, V2, V3. So this thing is a multi-map. So in a multi-map, you do not need to have all these tuples of the same sizes. They can be of varying lengths. So now the question is, what are then encrypted multi-maps? So encrypted multi-maps is just this multi-map, which is encrypted in a way so that you can query on it. So given a label, you can fetch these results out. So you are now working on encrypted data, okay? So encrypted multi-maps, they support a query operator. They also support an add operator. So for example, if you add a tuple T prime to a label, it produces a modified encrypted multi-map. So for example, if you add V3 to L3, V4 to L3, the value will be added to L3. And in case L3 did not exist already in the multi-map, that will also be initialized. And the delete is the opposite. Okay. Because we want to make these constructs practical, it's possible that there is some leakage in these operations. And this is well studied in encrypted search literature, that these encrypted multi-maps might have some leakage when we operate on them. So in this talk, I'm not going to specifically say what the leakage is for my constructs, because I think I'll not have much time to go in this detail. But the idea of security is that a multi-map, an encrypted multi-map, is called secure. I don't know if you're familiar with MPC definitions, but the idea is that there are 2 experiments that you design, a real world experiment and an ideal world experiment, and you say that an encrypted multi-map is secure if these 2 experiments can be shown indistinguishable. And the simulator is just given this leakage L. Okay. So the question is then, how do you build encrypted multi-maps on top of blockchains? So there are 2 ways in which you can go about it. The first is that you can build just a new blockchain from scratch, right? So if you do that, you can optimize the performance, right? Because you're building it from scratch, and you can, from step 1, you can think about that, oh, you want to store encrypted multi-maps. So you might put in some features in your blockchain, which is optimized to support multi-maps, right? But of course, the question is that how would you do that? And the bigger problem is that there are already so many blockchains out there. So is it really worth it that coming up with one extra blockchain, right? Would then, if you come up with that new blockchain, would it be even adopted? Would people even use it? So that's always a concern. So the second way to go about is that you build a technique in which you are using existing blockchains and storing your multimaps on top of existing blockchains, right? So your technique can be legacy friendly, and the good thing about this approach is that you can then benefit from the existing blockchains network, right? So if people are already using it and you build on top of it, then there are higher chances that your approach would be used by people. However, then there is a downside that it might not have the best performance, right? You might suffer from the bottlenecks of the underlying blockchains. And of course, the question of how remains, and this is what we will answer in this talk. So let's just think about this how from a very high level perspective. So because our approach is going to be legacy friendly, so you must think about this question that because generally blockchains are designed to store financial transactions, right? And now you want to store arbitrary data on blockchain. So how would you do that? That's the first question to think about. And the second is that even if you somehow manage to, let's say, store an encrypted multimap on top of blockchains, then how do you add or delete, right? Because by design, blockchains are tamper-proof. So how would you change your multimap, which is a desirable property? So let's think about the second one in more detail. So let's say you come up with a way of storing an encrypted multimap on blockchains. I'm not saying what way, but just think that there is a way that you have stored this. Now, let's say every time you want to add or delete, what you do is that you construct an entirely new encrypted multimap, EMM prime, and then you store it on the blockchain. Right? This is possible, right? You first download this initial encrypted multimap, update it in whatever way you want to, and then just push the new encrypted multimap back on the blockchain. So the good thing is that it will have a good query complexity because now you don't have to worry about this old structure. You can always just talk to the most latest version, right? So there will not be any problems or inefficiencies that will be created by add or delete, because this is just a fresh encrypted multimap, right? It's as if you started from this point. But of course, as it's very obvious that this is a very, very bad update complexity, right? If you're just deleting one value, you're doing so much of extra work. You're downloading, then uploading. So this is bad for update complexity. So there's a third thing that you need to think about is that how would you sort of achieve a trade-off between these efficiencies, different types of efficiencies like update efficiencies and query efficiency. Right, so these are the things that you need to think about. Okay. So what we do in our work is that we came up with three approaches, LSX, TRX, and PAX. These are three schemes that I'll describe, and these all have different trade-offs between different efficiencies. So we measure our schemes on, of course, time complexity and round complexity. Round complexity is the number of rounds between the client and the server. In this case, the nodes, the blockchain network. Then what do we do is that we measure round complexity in two different parts. The round complexity for reads and round complexity for writes. And the reason that we do that is because when you talk about blockchains, the writes are very, very expensive. right? So once you have written a write, to be sure that that write will persist, it might take a lot of time, right? For example, in Bitcoin, your transaction has to stabilize. It has to become 6 blocks deep so that you can be assured that it's not gonna be overwritten. Like some other chain will not be the longer chain, right? So this is why we partition our round complexity in 2 parts, for reads and for writes. And we call this round complexity for writes as our stabilization complexity, just renaming it because that made more sense in context of blockchains, because writes are associated with some sort of stabilization. Okay. So now I'm just gonna talk about very simple approaches of how you can store data structures in general on blockchains. So first I'll talk about how you can store a linked list, and then I'll talk about how you can store a tree structure. So let's see about linked list. So let's say you have this linked list that you want to store on blockchain. So what you do is that you take your V1, you create a transaction in which you store your value V1 and you concatenate it with bot. So because there is nothing before V1, so there is no pointer that's pointing to something before V1, right? So that's why it's a bot. And you create a transaction, you send it to the blockchain network. And then you store with yourself the head. Head sort of represents the address at which this transaction is stored. I'll talk about concrete instantiations of head, as in what this head will look like in real life. I mean, what these addresses will look like in real life. But for now, just imagine that it's some address of this transaction. So if you give to the blockchain this R1, you can fetch this back. Okay. So now when you have V2, you want to store V2, what you just do is that you store V2, concatenate it with R1, which is the address of this transaction, and you update your head, right? And this gray link sort of logically represents this chain structure, right? So if you fetch this transaction out, you can fetch R1, and using R1, you can fetch this transaction out. So you're sort of logically building this chain on blockchain. Similarly, when you have V3, you can do the same thing, append it with the address of this transaction, update your head, and so on and so forth. Right? So this is how we can store a linked list on a blockchain. But you notice here that the thing is that you cannot store V2 in a transaction until you know what R1 is, right? So if you want to keep on maintaining this logical chain structure, you need to know the address of the previous transaction. Similarly, here V3 cannot be stored unless you know R2, and so on. So because of this linear dependency, the stabilization complexity of storing a linked list on the blockchain actually is the length of the linked list, right? And I'll just remind you again that the stabilization complexity was the number of write rounds that client does with the blockchain network. Okay. So now if you have to extend this model to a tree structure, it's just the same thing. Suppose you have V6, V4, V5, which are already stored on the blockchain. Then if you want to store V3, now instead of just appending the address of one predecessor, now you have 2 child nodes, right? So with V3, you will append both R4 and R5, where R4 is the address of V4 and R5 is the address of V5. So now you're sort of building a tree structure on blockchains, right? So now similarly, R6, one address will be bought because v2 doesn't have a right child, right? And you can extend this, you can keep on doing this. So now if you notice that there is no dependency between v2 and v3, right? v2 is just dependent on its child nodes, which is v6 in this case. So what this means is that what the client can do now is that it can write all v6, v4, v5 in parallel. It can create all the three transactions together and send it to the blockchain, right? Oh, so similarly, it can do it for v2 and v3. So once v6 is stabilized, it can do v2. v4 and v5 is stabilized, it can write v3, right? So what's happening now is that all the nodes at one level of the tree can be written in parallel. So because of this thing, the stabilization complexity comes down to logarithmic in the number of values in the tree. I'm assuming that the tree is balanced, right? So now that we know how to store lists and how to store trees, now we'll go ahead and see how these three schemes work. They're just simple modifications of the techniques that I just described. So for LSX, let's say you have a multi-map. This is what you want to store, right, on the blockchain in an encrypted way. So let's say this was your multi-map. So what we will do is that we will represent each label as a separate list on the blockchain, right? So V1 and L1 will have its own linked list on the blockchain. L2 will have its own linked list on the blockchain. So for example, here, if you see pink ones represent L2 and they form one chain, and blue ones form another chain, right? So, oh yeah, and with the client, what you then store are the two heads, right? So at client, the space complexity would be the number of labels in your multi-map, because you have to store those many heads at the client. And actually, if you look at encrypted search literature, most of the dynamic schemes which are efficient, they actually use this much of a space at client side. Okay. So now, once you have stored your multi-map on blockchain, the question is that, well, I wanted to store encrypted multi-map, and it's actually very straightforward. All you have to do now is that you have to just encrypt these values. So before creating the transactions, you encrypt all the values and then put them in a transaction and then send it to the blockchain network. Okay. So then if you want to add, let's say V4 to L2, what you essentially do is that you create a new transaction, V4, append to it R32, R32, which is the current head of L2, and you just update the head. That's addition. If there were two values, so you would have created two transactions. And delete, to delete a value, it's just deletion by addition. So it's lazy deletion policy. So what that means is that when you have to delete a value, you add to the blockchain, but just put an identifier there to say that, oh, this is the value that's deleted. So here, as you can see, when I wanted to delete V1, I added it to the blockchain, but I set this delete flag. And I update my head. Oh, this has to be blue. Sorry about that, because I am deleting from L1. And then when you have to query, you just follow the chain of pointers, the logical pointers, right? So for example, when you have to query L1, you read this transaction, decrypt it, fetch the address of the last transaction, which is this, fetch it, decrypt it, compute the address of the last transaction, which is this. So you're just following the logical chain back, getting each and individual value and decrypting it. And finally, you can just remove the values which have their delete flags set. Okay. So time complexities for addition and for deletion, it is optimal, right? Because you do as much work as the number of values that you're trying to add or delete. If you recall, T was the size of the tuple. So you do that much of work, which is optimal. However, when you query, that's pretty bad, right? It's the number of values that you ever added or deleted. And the reason is because you're really never deleting the values, you're just adding more and more values. And the stabilization is, we already saw it for a linked list, right? It's a stabilization complexity was the length of the linked list. So in this case, the length of the linked list will be the size of the tuple that's passed as an argument, right? So that's O of T. So as you can see that these three things are bad. This is especially pretty bad because you'll just keep on increasing the length of your linked list ever. So queries will become slower and slower. So what we do in TRX is that it's a tree-based scheme, and the idea is that instead of now storing the tuples, the values in the tuples as list, you store them as trees, okay? So as I already mentioned that now you're storing values as trees instead of lists, balanced trees actually. So now what will end up happening is that now there will be chains of trees running around, right? So earlier you have chain of chains, right? For every add, you had created a smaller chain, right? And what you were doing essentially was that you were sort of linking one chain with the previous chain by linking the heads, right? So here now you're creating different trees and you are linking the roots together. So this figure over here denotes what happens if there were two labels in your multimap, let's say. So one is blue label, it has chain of trees, and then another is a red label, which is another chain of trees, right? And one tree represents the values that were either added or the values that were deleted. Okay. Oh yeah, so I should point out that just by doing this change, you have brought down your stabilization complexity from linear to logarithmic, right? Okay. So the third scheme is PAX. So what it does is that it tries to optimize the query complexity. So TRX and LSX, the first two schemes, they had bad query complexity, right? So PAX tries to improve this. So let's see. So the question is that why was the query complexity so bad? It was really because of lazy deletions, right? Because when I deleted V4, I really did not delete it, but I appended something. And then during query, I read all of these things, right? But if instead somehow I can, while querying, while the query operation is going on, if somehow I can skip over the deleted values, I can see some improvements, right? And this is what we call as patches. So patches actually help us to jump over the deleted values. So when V4 is deleted, I create a patch from V5 to V3. And when V2 is deleted, I create a patch then from V3 to V1. So now if I query, I can go from V5 to V3 to V1, okay? So the question is that, okay, you're creating these patches, but where are you storing them? And on So the answer is that on the blockchain itself in a separate list, and we call it the patch list, right? And we already know how to store the lists. So how does a patch look like? It's just this data, which is saying go from V5 to V3, go from V3 to V1. It's just simple data, right? And we'll use this data to do these jumps. Okay, so now what happens when V3 is deleted? I create one more patch, let's say from V5 to V1. Now, as you can see that there are two issues if we do this. The first is that there are now two patches from V5, right? Which one is the correct one? While querying, I should take the correct one. If I took the patch from V5 to V3, I'll end up reading V3, which is not good. So my correctness is in danger. The second issue is that my size of patch list is becoming linear in the number of deletes. So this is as bad as having, doing lazy deletes, right? So what I really need is that I somehow need to delete these redundant patches. So I need to get rid of V5 to V3 and V3 to V1 after V3 is deleted. So this is called cleanup of patch list or patch structure, which is what is needed. So, but this looks like a chicken and egg problem, right? To delete from the multi-map, I need to delete from the patch list. So there is a circular dependency there, right? To break this dependency, what we did was that we used a different technique, which is called copy on write. And this is what we would use to delete from the patch list. So here is the idea. So suppose you have a list of patches that you have stored on the blockchain, right? And you want to delete P2. So what you can do is that you can create a copy of P3. So this node over here has exactly the same content as P3. The only difference is that it, instead of pointing to P2, now points to P1. However, if you do that, now you need to update P4. Again, the content is the same, but it needs to now point to the new P3, which is P3 prime. Right, and you can see this problem will go on. And in this case, if you now need to delete a patch, which is very deep in the list, you will have to modify all the patches that were stored after P2. So this is expensive. And how do we solve a long dependency problem? We create a tree. So now the patches are organized in a tree structure instead of a linked list structure. So now if you delete P5, you just have to modify logarithmic number of patches that are on the path to P5. So you just need to update P3 and P1, right? Okay, and we can show actually that the number of patches in the patch tree will not be too large. So in particular, they will be not more than the number of values in your multimap, currently in your multimap. So I'll just now summarize the complexities. This was our PAX scheme, and I'll summarize the complexities. Here I have mentioned the complexities of LS6 just for comparison's sake. So the time complexity is O of t, right? You're just appending the values. So, and this was optimal. So the delete, this is a little bit worse than what we had earlier. Earlier we had O of t, but now you have to pay some extra cost to create new patches and to clean up your patch structure as well. So that's why this logarithmic factor starts showing up. But it's logarithmic in the size of the multimap, and size of the multimap are the values that are not yet deleted. So current multimap. And query complexity, it actually becomes optimal. This is the size of the multimap. These are the values that you want in your answer. So you have to do this much of work to read this, and it actually becomes optimal because now you are essentially jumping over all the deleted values. Unfortunately, the stabilization worsens. It goes back to O of t. Remember in TRX, because we could create those trees, so we brought down the stabilization from O of t to O of log t, but in this, it goes back up. It goes back to O of t. Okay, so now, I'll just pause for a minute, and if you have any questions, I can take them, or else I'll just move on.
I can ask a question.
Yeah.
Can you go back to this slide? I think it was like page 50 or 49, where you had these patches.
Please
Not
pause
this
me.
One. Yeah, this one.
Mm-hmm.
For this one, I didn't get the issue with this, like having these other patches that goes from V5 to V1, because once you put your head to this last one, V5 to V1, you will always skip the other ones, right? Because I mean, your head is here, and once you fetch V5, sorry, that will always direct to V1, right? So you will always skip the other patches. I didn't get the issue here.
Right. Okay. So here, it's possible that there are other patches over here, right? Before V5 to V3, there might be other patches over here. And this is a list that you're creating, right? So if you do not delete these patches somehow, then you will have to at least do the work to read all of them. And then, okay, you can have this strategy that, oh, if I see V5 to V1, I'll ignore this, but at least you'll pass through them, right? So you're doing that much of work.
But isn't your head at V1 to V5?
Yes, but this is not stored at client side, right? This is stored at in blockchain. So let's say there was a patch here, a good patch, which you needed. So for example, suppose there was a node here.
Yeah, if we need that one, okay, yeah.
If you needed, there was a good patch which you needed. So you will have to go through these useless patches as well to fetch that good patch as well.
Okay, yeah.
Okay, yeah, thank you.
Yeah, another question, follow-up question on this patch is that, so because you later you have the optimization to store this, I mean, this list to still like a tree structure. So I'm not sure if later you have further updates, addition or deletion, will the tree be rebalanced or rebuilt?
Oh, so I did not specify that, but that tree is stored in a balanced way. So if you are delete, okay, let me just go to that slide quickly. So when you do that, when you delete P5, it's possible that you might have to do some rotations to restore its balance property. Is that what you were asking?
Yes, but yeah. So then the another question is that because when you do the rebuild, everything is actually needs to reflect it on the blockchain because the tree, this patch tree is also in the blockchain, right? So will that cost a lot of? I mean,
so you will actually, we can show that you will not update more than 3 parts.
3 parts.
3 parts after rotation. Okay. So the idea is that if you're using, let's say, arbitraries or something, there are some constant number of rotations that you need to do, and that only touches just a small portion of the tree. So it's not that you will have to rebuild the entire tree from scratch.
Okay. So because you have the rebuild, so I'm not sure whether it is still like I mean, advanced or have benefits compared to the lazy deletion, because lazy deletion doesn't have this issue, right? They just, I mean, needs to fetch, I mean, more deleted entries when you do search.
Right.
Yeah.
Right. But let's say if, as we saw, that the query complexity is then ever growing, right? It's the number of values that are ever deleted or added. So this can save you time while querying.
Okay.
So you're paying extra at deletion time, as we saw in that there is an extra factor in delete efficiency, that logarithmic factor, but you save on query. But you're right that when you start implementing these things practically, this actually might affect your efficiency, and we'll see some plots, some graphs.
Yeah, thanks. And another question is related to the very basic, I mean, the construction of the linked list, because you mentioned that the right round may be, I mean, the bottleneck for the blockchain, right? So I'm just wondering, because you are talking about the multi-key map, right? Where normally a label can associated with several values. And now you basically split those values into like key value pairs, right? And each key value pairs is in separated blocks, right? So I'm just wondering whether you do this separation, why not just, I mean, store all the values, I mean, in one block, or couple of values in one block, so to avoid those values stored into different blocks, so that later when you do search, you just have like a O1 complexity.
Right. So that's limited by the size of the transactions that blockchain is allowing you. So we will talk about packing if I have time left.
Okay.
Yeah, but packing is something that you can do, is that instead of splitting just storing one value in individual transaction, you can start storing multiple values. But again, that's limited by the size of blockchain. It's not necessary that you can store the entire tuple in one transaction, but yes, you can get away by creating a lesser number of transactions, for sure.
So basically you assume that the values are like, I mean, each value is very small. The size of each value is small. So, but I mean, if you consider the value actually in the NoSQL database can also be very huge. So maybe one value cannot be stored in one transaction either.
Yeah, it's possible.
Okay, thanks.
Okay, so now let's come to the deployment part and some experiments that we did. So we implemented these algorithms on Algorand and Ethereum. And so here were some things that after implementing, after looking at our results, there were some things that we thought about. So the first question that we needed to answer was that, what are these addresses anyway? So let me just move this bar. Okay, yeah. So if you remember, in our approaches for chaining purposes, we are using these addresses, right? We are concatenating our values with the address of the previous transaction. So now when you're implementing it, you have to answer this question that what are these addresses? So the first thing is that they can be transaction hashes actually. So if that is the case, what will end up happening is that your LSX, the first list-based scheme, is same as the tree-based scheme, philosophically speaking. So if you remember, the reason that we went from LSX to TRX was because we wanted to improve the stabilization complexity, right? We wanted to parallelize the creation of transactions at each layer. right? But if you're using the transaction hashes as your addresses, then the client can just, even in the linked list case, right, it can just create all the transaction hashes on its own. It doesn't need to talk to the blockchain network, right? So in which case the stabilization complexity only actually becomes O of 1, because then you can just send everything, send all the transactions at the same time in just one round, right? However, there's a problem. The problem is that many blockchains, actually, I do not know of any blockchain who indexes using, who allows you to look up using transaction hashes. The problem is because then the nodes have to keep a database of transactions for the fast lookup purposes. And that's why, and that requires a lot of memory, and that's why they do not allow you doing that. And if that's not even allowed, so other option for you is to use block numbers as your addresses. And actually most blockchains do allow you to look up blocks by their numbers. So once you know the block number, then you have to sort of parse, of course, all the transactions and then filter out the transaction of your interest. Can someone please tell me how much time do I have?
Ten minutes, I think.
Okay. Of course, but this requires higher bandwidth, right? Because now you're downloading the blocks. And we did this on Algorand, and as was expected, when we used block numbers as our addresses, it was way worse than if we were using transaction hashes. So transaction hashes was almost had much lower slope than if we were using block hashes. But and of course also notice the difference between the two, like LSX with block hashes and LSX with transaction hashes. And this gap was really reduced if you started using TRX, right? And this made sense because in TRX, there was already a feature of parallelism built in, right? That's why the gap between TRX block and TRX transaction hashes was way lower because of its logarithmic stabilization. And the second thing was packing, as someone mentioned, that you do not need to create a different transaction for individual values, right? You can start packing things together. So if your transaction size is allowing you to store 3 values, go for it. Store 3 values together, right? This will save you time because now you are reading and storing lesser number of transactions, and also the money, right? Because for every transaction, you might have to pay some fixed cost, which you can now avoid. Unfortunately, Axe doesn't support packing. And this is what we actually want to now work on, that how to incorporate packing into packs. And this has really adverse effects, as someone again pointed out or expected to happen. So these lines over here represent packs in some model, whether we are using blocks, block addresses, or transaction addresses, and things over here, they represent TRX. And you can see that packs really perform very poorly. Even when asymptotically, packs had optimal query complexity and TRX had really bad query complexity. Still, TRX is doing much better than packs, and just because of packing. But then we just extended our experiments to see whether the complexities ever kick in. And it actually happens. if, let's say, you delete almost all the values from your multimap, but leave a few in there, then PAX starts having really good query complexity, while TRX doesn't, right? Which was expected because of now the complexities start kicking in. And I think because I'm running out of time, I'll just not talk about it, but the idea was that why can't you just store the multimap in smart contracts and do the operations on the multimap using smart contracts functionalities. And the problem is that it's more expensive and not all the blockchains support complicated smart contracts functions. So it's possible that you might not be able to do this sort of a work using all the blockchains. So some future directions. First of all, we really want to improve PAX. We want to add packing to it to see if it really can start performing well, because its asymptotics were good, but in practice, it just doesn't perform well. Improve its stabilization. If you recall, TRX had logarithmic, while because of in PAX, it was linear. So bring that down as well. Another interesting thing would be to implement it on Bitcoin. We really wanted to do it, but it was really close to the deadline and we just did not have time. So we just went for Ethereum and Algorand. But it'll be nice to see it, it'll be nice to implement it on Bitcoin as well. And finally, do some thorough comparison with how this compares to, let's say, Ethereum's smart contracts, which actually provide you like Turing complete languages. So yeah, I guess that's all I have, and I'll be happy to take any more questions.
Thank you very much, Archita. It was a really great presentation. I really enjoyed it, especially the T-Rex and the chicken. They were wonderful. Yeah. So do we have any questions from the audience?
I just want to ask a simple question. So have you considered the forward and backward privacy of your schemes?
They are not forward private or backward private. And the problem is that because of the linking, because the way they are linked, and at query time, you just touch all of them. So you just break your forward and backward privacy. They are not, yeah. It'll be nice to sort of extend them to have forward and backward privacy.
Okay, thank you.
Hi, thanks for the presentation. It was really interesting. I'm just wondering, did you consider single writer, single reader setting, or do you have like any future plan to consider the scenario to be multi-user? Because according to my understanding, it was all single writer, single reader, right?
Right. So let's see if we can somehow, let's say offline, there is a way to exchange the keys.
Then there is a challenge regarding the taking care of the state of the database, as well as how we are going to know what modification has been done by who.
Right. So I think the problem is the state of the client. So we are maintaining at the client the heads, right, which is the state essentially. Yeah. And I think even if you go to encrypted search world, where in dynamic settings where you are allowing for updates, the client actually maintains the states, right? And that's always an issue to extend it then to the multi-user setting. So yeah, I think it'll be interesting, but we have not yet thought about it. We are right now we are looking more for getting actually forward and backward privacy and getting PAX to improve.
I see. Thank you so much.
any last question which you can think?
I can maybe ask a quick question. So in terms of the costs on the blockchain, are these approaches, or are they all more or less the same, or did you consider the costs on the blockchain of different versions?
You mean money-wise?
Yeah, money-wise, and maybe the number of blocks that has to be put on the blockchain because of this database and so on.
Right. So yeah, we implemented on the testnet because of course we didn't have that much of money to go on mainnet. So, but in terms of storage, Ethereum is better because it allows for bigger transactions. So you can store a lot of data in just one transaction. So in that way, Ethereum is better than Algorand. But it'll be nice to see what happens to Bitcoin, because as far as I know, Bitcoins provides, like you have to do some tricks to store arbitrary data on Bitcoin, because it was not really made to store arbitrary data. So the transaction size are really small for arbitrary data in Bitcoin. So I think in Bitcoin, it'll be even more space that will be needed. For money wise, I think Algorand is the cheapest, but I will, don't quote me on that. But yeah, I can guarantee you for storage, storage wise, but not too sure of price wise.
Okay, yeah, thanks.
Okay, so I would say that's all. Time is all up. Thank you very much, Archita. It was a really great presentation. I really enjoyed it. I'm pretty sure all the other listeners also enjoyed it.
Thank you for having me. It was nice to talk to you all.
Thank you very much.
Thank you.
Thank you.
Bye.
Bye.